All right, everybody, so welcome back from your summer. Everybody have a good summer for the most part?
Yes, you can say that.
Guess I can say it. Okay. All right, so welcome to Mechanics of Deformable Bodies at 8 o'clock in the morning. I can see you all are having a hard time containing your excitement being here so early. Um, in case you don't know me, my name is Dr. Michelson. I'm going to be your instructor for this course. We're going to go through a little bit of housekeeping today, just some of the nuts and bolts regarding the class. We're actually going to start a little bit of the lecture today, just because we meet 2 days a week. I want to about to drop that. I just want to make sure that we're using our time as best we can. So real quick, let me just get some of this stuff out of the way. So we are here at 8 o'clock in the morning, so I do want to give you at least a little bit of incentive for coming here. So I do have a small attendance grade in the lecture, or in the grade. Also, I don't know if you all can see this, but I've got this little lapel mic on right here. What I'm doing right now is recording the lectures, not only the audio, but everything that you see on the screen. And I'm going to use the SmartBoard software to do all of the examples. So everything that you need will be on the screen. The reason why is I'm going to take all of this and post it on one big YouTube playlist, so that if for some reason you miss a day or you didn't understand something or miss something in class, you can come back and cover what you need. So everything will be available, and it'll all be on MU Online. So I use MU Online, or Blackboard, whatever you want to call it. I use that pretty regularly for posting things like homeworks, posting your grades, the syllabus, all of that stuff. I'll be honest, I probably won't post your attendance every day, because I'd have to, keep up with that every day. I mean, I'll keep track of it, but I don't know if I'll post it on MU Online. But I'll make sure and have all the other grades posted as well. Okay. What else? Textbook. We've been using this textbook for a while now with this course, so if you don't feel like buying one, I'm sure you can probably find someone that'd be willing to let you borrow it. I mean, we've been using this book, I think, now for at least 2 years, maybe a little longer, but the book's been out for a while. It's a good book. So I do recommend getting it, just because this is a pretty important class that you'll take throughout your degree here. But I leave that to you. At the very least, I would consider getting something. But then again, maybe my opinion will change over time. And when we've got Google now, and everything's on Google, so you can probably find just about anything you need online. So, okay, homeworks. I say here that homework's assigned on a weekly. I usually like to assign homework on a weekly basis, but sometimes that's not the case. Usually, for me, I assign homework when we finished a topic, when it makes sense to cover it for a given topic. I'm not one of those guys that will give you a homework assignment every single day, and then it's due the next day. I'm not like that. I mean, we might have 8 or 9 homework assignments throughout the semester. Now, there'll be larger assignments, but I think it makes sense to wait until we've covered a given topic, give you an assignment on the whole thing, and then move on and talk about something else. A little bit on format. Just make sure that just for the cover sheet, just use the original assignment handout as the cover sheet. Make sure you're using quad paper, no notebook paper, and just make sure that you've got neat handwriting that I or the TA can read it. Also, straight edge is probably a good idea, not just for the homeworks, but for the exams. In this class, you can tend to draw a fair amount of diagrams, so it's nice to have a straight edge on you. What else? Okay, so exams. I'm a 3-exam guy. I'm not a 2-exam guy. I don't like to do a midterm and a final. I like to break it up into 3 exams. I think that reduces the stress level a little bit on each test. Each exam is worth 20% except for the final, and it's worth 25%. And it's not because I think the final is more important. It's just because the way the topics break down in the course, there just happens to be a little bit more stuff on the final, so I think it deserves a little bit more credit. It's not a whole lot more, but it's just sort of the way the topics break down. There tends to be a little bit more on the final. Now, one other thing about me, I'm really not a comprehensive exam guy. I don't believe in that. We'll have exam 1 on, it'll be axial forces and torsion, and you won't see it on exam 2 or 3, okay? Now, with this course, and it's not as true as others, but there is, some instances where some of the material sort of bleeds over into other tests. I do my best to try and avoid that, but sometimes it is what it is. I mean, this course, one of the biggest topics that we will be dealing with is the concept of stress, which we're going to talk about today. You'll see stress on every exam. I can't avoid that. But be prepared. I have a fair amount of cheesy and corny jokes to deliver at 8 o'clock in the morning, so I can tell you all are going to appreciate that this semester. But yeah, I have a significant number of them. I do let you all use a formula sheet on the exams. You all can put whatever you want on that formula sheet. The only thing I ask not to go on the formula sheet is worked out examples, because in many classes, and this class is one of them, you put worked out examples on your formula sheet. What ends up happening is you get so focused onto this one example that you are on the test and the example's a little different, or the problem's a little different, and you get sort of mixed up in it. If you just focus on the formulas and the methods that we learn, you're going to be fine. Okay. Anybody have any questions so far? Anybody have any questions so far? Yes, sir. Oh, yeah. I saw a couple people come in. Who didn't get a syllabus? All right. There was a couple back here. Okay. Now, I made this joke yesterday, instructional analysis, and I'll go ahead and make it again in here. I almost think that our curriculum should be treated like the menu at a Mexican restaurant. You go to a Mexican restaurant, and you look at the menu, and there's some items on the menu that have a chili pepper next to it. What does that mean? Those are spicy meal. You better be aware of it. Well, some of our classes should have something like that. That indicates whether or not the class has calculus in it, because I bring up that word and everybody goes, not calculus. This class is going to have a little bit of calculus in it. I don't want you to be scared of it, because the calculus that we do in here is really basic, really straightforward. What's the derivative of x squared? You're good. Seriously, it's pretty basic stuff, so I don't want you to get nervous or worried about it. I also want you to be prepared for it. I want you, when you see it coming, go, oh no, not that. We are going to see it here and there, and it's not just to throw it in there for calculus sake. Some of it we actually need. For instance, if you've got an axial load on a bar and the bar changes in cross section, like it gets narrower, you actually need calculus to figure out how much it stretches and things like that. We're going to see a few derivations, some mathematical derivations. We're going to see some geometry, some trig. So I just wanted you to be aware of that, just so everybody's clear on that. Any questions? Okay, before I get into the material, let's see. Let me pull up the syllabus just so you all aware of a couple things. So my office is 2227, which is on the second floor, down that hall, last office on the left. So pretty easy to find. Just right down that hall on the other end of the building. Excuse me. My office hours are Monday, Wednesday, and Thursday. I mean, I'm usually here a fair amount. The reason I did this is on Tuesdays, there's a good chance that on most days I won't be here for the most part of the day, because I've got a class. I've got class at 8 a.m. and then I have a class at 6:30 at night. So there's a good chance I'll probably go home and then come back later. So if you don't see me in the middle of the day on Tuesday, that's probably why. Let's see. Let me go to the last page. Because this is a Tuesday and Thursday class, I like to do a little bit of a somewhat comprehensive job in determining our schedule for the semester. Now, like I say here, day one is just the overview of the course, and then on day two we start talking about stress. We're also going to talk a little bit about stress today. So some of these topics may bleed over into other days, but I do my best to try and give you a breakdown as to what we're going to cover each day. A couple things worth mentioning. You notice here I've got exam review days scheduled in. What I like to do on exam review days is I come in, I'll give you a short little PowerPoint of specifically what is going to be on the exam, And then I sort of shut up and let you all ask whatever questions you want. And we can spend the whole day, we can do example problems, we can go over your homework, you have any questions about the notes, whatever. I let you all run the show for a day and let you all ask whatever you want. Now, you can ask me what the answer to problem 1 is going to be. I'm not going to tell you. But you can ask whatever you want, and I'll do my best to answer your questions because I want you to be prepared. So that's point 1. Point number 2, I did my best to sort of divvy up the exam days such that we were splitting up the topics as appropriate and also trying to evenly distribute it throughout the semester. Now, just a heads up, I have tentatively exam 1's going to be September 27th. If you come to me like a couple weeks before that and say, okay, so here's the deal, we've got like 8 exams that day, can we move it? Absolutely, I have no problem with that at all. I'm a pretty easy guy to get along with. But don't come to me, after class on Thursday and say we need to move the exam, because then everybody's already planning for it for Tuesday. So I'm a pretty easy guy to get along with. Just make sure you're giving me a heads up. Sound good? Now, another thing, this is tentative. I've got a couple travel dates throughout the semester. I've got to go to Omaha and then to San Antonio in October and November. So depending on that travel, we might have some days where we don't meet, and we'll come back and pick up some of these topics later. So, but I'll make sure and give you all a pretty clear heads up. All right. Any questions so far? Okay. Now, I haven't uploaded anything yet to Blackboard, but if you go to Blackboard, like this is for structural analysis, so this is a different course. But if I go to Blackboard and I pick, I'm using structural analysis as an example, and I go to, where is it? Course content. Wait, where'd it go? Did I go crazy here? Where'd course content go? Hold on. I think it's because I'm looking at it in faculty view. Anyways, when you go to course content, you'll ultimately see a list that says YouTube playlists. Click that, and there'll be a playlist of every lecture. Okay, now I'm going to upload it today, and there'll be only one video once this current recording processes. But throughout the semester, this will populate. So if you miss a day or if there's something you need to review, everything will be there. Sound good? Okay. All right. So let's see. All right. So before I continue, any other questions? Anything go on? Or okay. I'm going to get a sign-in sheet started if you want to start this and sort of meander that around. I do want to get a little bit into some of our topics today to sort of emphasize why you're taking this class. It's always something I like to at least get out of the way on day one. If you're going to be here at 8 o'clock in the morning on Tuesday and Thursday, there better be a good reason for it. So I at least want to try and allay some of those concerns today. 1, 2, 3, 4. All right, there's that. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then 1, 2. Just a heads up, I like maybe a week before exams or a little earlier, what I'll do is when exam time comes around, I'll come to class with like a 3-ring binder, and it will have all of the handouts that we've distributed to date. So if you're missing something, let me know, and I can have it printed off for you before the next class, because I want to make sure you're prepared for the exams. So, sound good? Okay, all right. So I brought some props with me today, and hopefully that'll kind of explain, or I'll explain why I brought those and why they matter. What I want to do for this first little bit is I want to get into what we're doing in this course and why we're doing it. Okay, so I want to present to you a couple of scenarios. Okay, so let me start off with this. Okay, so I have here a standard paperclip. Okay, now I'm a reasonably strong enough guy that I can take this and I can permanently deform it. Okay, it's permanently deformed, it's bent, it's not going back. Okay, now I also have here a bar that's arguably, or for the purposes of discussion, made of the same material as that paper clip. You think I can do the same thing to this? I'm good, but I'm not that good. Why? Why can't I do the same thing to this? It's dense, but it's simpler reason. It's bigger, okay? So let's look at this example. So what I've got here is I've got two elements, okay? These two elements are made of the same material and the same things happening to them. Now this first one above, let's say that once I start loading this and I hit 100 pounds, the thing snaps. Is the same thing going to happen down here? No, okay? Very clearly not. Because what matters from a behavior standpoint isn't really the force that we're applying. It's this concept called stress. Instead of, the 100 pounds, it's the 100 pounds per, square inch, whatever the area is. You've probably heard the term pressure before, and that's probably the first thing you're thinking of is pressure, force per unit area. We really don't use pressure when we're discussing mechanics of deformable bodies, and the reason why is pressure is reserved for things like fluid mechanics, like liquids and gases. And here, where we're dealing with solid mechanics, taking some object and applying some load to it, we refer to that as stress. I mean, you can argue it's kind of, related to the same thing, but that's where the difference is. So if you hear engineers or anybody talking about pressure, they may be talking about water pressure or air pressure, things like that. Stress is related to solid mechanics, things like beams and columns and gears and things like that. So so going back to this example, because it's the stress that matters, that's sort of a mathematical description that can kind of explain what's going on. This element, while it has the same force applied to it, it doesn't have the same stress. And kind of an easy way of thinking about it, if this rod were 3 times bigger, you'd have to have a load of 300 pounds before it would fail. Make sense? Straightforward. Okay. All right. So that's scenario number 1. Scenario number 2. Okay. Now, just so you all are aware of what these are A505 tension specimens. How many of you all are in 215, engineering 215, or have had 215? Did you all do tension tests in that class where you took a piece of material and yanked on it? Did you test them on these? What's that? You're in it. Are you in it? Pulled them apart. Okay, so you've seen these before. Okay, so these are material specimens, and they're meant to evaluate the characteristics of a given material. So this is a sort of a metallic alloy type tension specimen. This is a composite polymer, like a plastic or something like that. Now this is a different scenario. These are the same size. I mean, they are almost exactly the same size. I mean, there's a little bit of damage to this one. For the purposes of discussion, we can say they're the same. These are manufactured to be identical. So now the geometry is the same. So let me ask you this. Let's just keep it simple. Which one do you think is stronger, the alloy or the plastic? The alloy, okay? Now I'm confused because this is different than scenario number 1. Those were different sizes. So if these are the same size, why does it matter? It's because it's a different material, right? So we're starting to hone in on a couple things that are going to be kind of important. It's, for scenario number 1, what mattered was the geometry of the situation. The second rod was bigger, so the stresses were different. Now the second parameter that matters is the material itself. Even though the geometry is identical, the fact that they're made of 2 different materials is going to change the response. These 2 different materials have 2 different properties associated with them. And those properties are going to change, how they respond, and ultimately the calculations we do on them later on. And it's, it's other things. Like if I go back to, my paper clip, materials respond in different ways. Like if I take the paper clip and I apply a load to it, it starts to plastify and permanently bend. Okay? That's how a metallic paper clip responds. Now I've got a wooden pencil. Is this pencil going to do the same thing? No, if I do that, it snaps. Okay? It behaves differently. Why does it behave differently? Because it's a different material. Okay? So that's what we're going to try and assess today. And there's other things. You know, I have here a piece of flexible PVC pipe, and this is actually going to be what we spend a lot of our semester on. But one thing that can change behavior is just the way that we load it in general. For instance, I've got this PVC pipe. Now, I have a reasonable enough strength that if I take this pipe and bend it, I can actually visibly deform it. You can see it deforming, okay? Now, if I were to take it and stretch it, I mean, I'm pulling on it, but you really can't see it elongate. It's because this element has a far higher stiffness axially than it does flexurally, okay? And the way that we load things matter. They change the way that we assess them. They ultimately can change the way that we design them. So that stuff can really influence our designs to come. I mean, a lot of our course this semester is going to be looking at the different ways that you can load something and how it affects the response. Do I take an element? Do I yank on it? Do I bend it? Do I shear it? Do I twist it? Those different loads produce different types of stresses. And managing those stresses is the whole point of what we're doing here. You know, I don't mean to sound, you know, melodramatic or whatnot when I say this, but this course has the potential to be one of the most important courses that you take as an engineer. And the reason why is you go to any practicing engineer who does a fair amount of design, and it doesn't matter if they're designing highway bridges or they're designing gears, airplanes, buildings, what have you. You ask them, you know, about an open-ended design problem. I've got to design this 100-foot long bridge, or I've got to design this shallow foundation to support this building, or this gear to transmit this level of torque, whatever. And the first thing that pops into their head is, well, how big do those elements need to be to manage their stresses? And stresses is where all these concepts of design begin. I mean, you're engineers. The main purpose of an engineer is to design, to select components to safely, you know, meet their demands. A lot of that begins here. A lot of that begins with stress. So this can be a pretty important class. Ultimately, though, hopefully it's a pretty fun course. And I'll try and liven it up with, again, very cheesy jokes throughout the semester. I'll do my best. So a couple of other interesting points. This is just, you know, food for thought for later and stuff we'll try to assess. One of the things that can be kind of interesting is just looking at material behavior in general. Essentially the difference between elastic behavior and plastic behavior. Going back to the paper clip, this is what we call plastic behavior. In other words, what I've done is I've taken this paper clip and I've deformed it such that those deformations are permanently locked in. They're permanent deformations. Now, if I did the same thing to, say, a rubber band, what would happen? I take the rubber band, stretch it, let it go. What would happen? Go back to the way it was. Those are elastic deformations. Mostly in engineering, we try and limit everything to the elastic range. So if we put a force on it, load it, and let it go, it goes back to the way it was. And for the most part, we try and stay within that range. There are some instances where allowing a little bit of plastic deformation is actually a good thing. I'll give you an interesting example. So if you own a gun, or if you ever use a gun, one of the interesting methods that they use for manufacturing involves a concept known as auto-frettage. And what that basically means is you have a gun barrel, okay, and what they do to that gun barrel is they take it and they subject it to very large internal pressures, such that they actually cause the inside of that gun barrel to yield and permanently deform. And the reason why they do that is because they're trying to lock in some additional strength in that gun barrel so that when you fire a bullet, the bullet doesn't permanently deform the barrel. If that didn't happen, what would happen when you'd buy a gun? You'd buy a gun, you'd shoot a couple times, and then it would jam and it would never work again. So that's sort of an interesting concept where permanent deformations are actually a good thing. But that's just, you know, food for thought. Load orientation can matter. For instance, if I take this PVC pipe and I load it in tension, it's pretty tough. But if I load it in compression, it buckles. And elements tend to be far weaker in compression than they do in tension. And being able to assess that can be a really big deal. So that's going to be something we talk about near the end. And also, member orientation can be kind of important. And this is really important for things like beams. And we'll talk about this later. But if you've got something like I don't know, a porch in your backyard, it's elevated porch, and you look at the support floor elements under that porch, they tend to be oriented kind of like this, long way up, not flat like this. It's because those floor joists are stronger oriented in this direction than they are in this direction. We'll be able to express numerically why that's the case later on this semester. And lastly, things like multiple stresses. What if you have an element that's being bent and twisted and pulled on? How do you assess all those stresses happening all at once? These are all things that we're going to try and look at this semester. Okay. Anybody have any questions? Okay. This is the kind of stuff that I want to make sure that you're getting a clear understanding as to what you're doing in this class and why you're doing it. And if you've got that picture in your head, I feel like I'm doing a good job. Because throughout this semester, it's very easy in this course to get lost in the minutia, the math. Oh, this is gigapascals, not kilopascals, and it's easy to get lost in that world with losing sight of the big picture. I always want to make sure that you're kind of getting an understanding of the big picture, what you're doing in here, and why you're doing it. Okay, so let's talk about stress, which your college students, I'm sure you've dealt with it before. That was a joke, not a very funny one. What we're going to be doing is in this entire course is studying stress. You could almost say this, instead of calling this course Mechanics of Deformable Bodies, you could almost call it Stresses and Strains, and that's all we do. Main reason, though, goes back to that first scenario. If you have two objects that are made of the same material but they're different sizes, they're not going to fail at the same force, they're going to fail at the same stress. Okay? So I'm just going to look at a given structure. I've got a beam here. It really doesn't matter if it's a beam, a body, what have you. I'm sure you all have seen stuff like this in statics. Am I right? Something similar? Okay. So one of the secret weapons of structural engineering or mechanical engineering is a samurai sword or a lightsaber if you happen to be a sci-fi fan. What we try and do for the purposes of design is look at the internal forces inside a section. So we cut a section, and the idea is, so let's say I've got this table, and let's say, I don't know, I'm sitting on this table, and Austin doesn't like me very much, and he decides to get his samurai sword and or lightsaber, and he decides to cut right through this table. What's going to happen to me? All right. What's going to happen to his grade? There we go. Okay. We're on the same page. Okay. All right. The reason why that's important is because when he made this cut, he released the table's ability to resist certain forces right here. So at this point right here in the beam, there has to be some level of force inside the structure resisting the loads that we apply to it. There has to be some level of force right here. Otherwise, I would always fall down. Okay? And being able to quantify those forces is where we begin the purposes of design. Now, if we look at this from a static standpoint, in two dimensions, remember you've got sum of forces in the x direction, sum of forces in the y direction, and sum of moments. If we look at that from a statics perspective, technically there would be three potential forces inside a given element. We've got axial force, we've got a shear force, and we've got a moment. That just comes from x direction, y direction, and moment. So that's two-dimensionally. Three-dimensionally, we would get possibly six forces. We would get, three forces, or I should say six resultants. Three forces and three moments. Okay? Now, I've come up with a little bit of maybe different notations and stuff you're not used to. For instance, this force along the x direction, I'm calling that P. P tends to be our expression that we use for axial force. The moment around this direction, I'm calling that T for torsion, kind of because it's twisting the element. You see what I mean? And then I've got 2 shear forces and 2 bending moments, sort of bending it like this or bending it like that. So this is just kind of to express our notation that we're going to use throughout this semester. Sound good? Okay, all right. Now, what matters though, and what we discussed earlier when we were looking at the paperclip versus that bar element, is that it wasn't the force that mattered, it was the stress, okay? Now, this definition is really solely from a calculus standpoint to kind of help you understand what we're talking about. I'll just be frank, we're really not going to use this limit definition very much. It's really just going to be force over area for the majority of what we use through this semester. But if I wanted to get infinitesimal and I wanted to get analytical about it, really stress is the force per unit area. But really what I'm looking at is force per unit area at a given point, because I could have different stresses here than I do here, or that I do here, or what have you. So that's where the calculus standpoint comes into play. I isolate a little element and say, all right, the force over that element divided by the area over that element, and then take the limit. That's where I get stress. Now, for the purposes of notation, we really deal with 2 types of stresses in this course, and this will make sense as we evolve through it. We have normal stress, which is if I've got an element and it's, the stress is applied sort of normal to that plane. Shearing stress is if it's applied parallel to that plane. So if you've got normal stress results from things like, yanking on it, like pulling it or bending it. You get normal stress. Shearing stress comes from things like twisting it or shearing it, like that. That's where shearing stress comes from. And we can get all sorts of stresses, but these are really the 2 that we tend to deal with on a given basis. Sound good? Okay, all right. A little bit about units. So in U.S. units, we tend to deal with either PSI or KSI. Y'all have heard the term KIP, right? KIP being 1,000 pounds. Okay. We tend to see KSI a lot more because, we can get some pretty large stresses. For instance, tire pressure is, 32 PSI? We can very easily deal with things like 32,000 PSI, on given beams on bridges or what have you. So, I tend to use KSI a lot more. That's just me. In metric, we deal with pascals. Newtons per meter squared is a pascal. We also tend to use this quite a bit because we tend to deal with pretty large forces, number one. And when we look at things like deflections, like if I've got this table and I've applied load to it and it deflects, we tend to express that deflection in millimeters. And a quick conversion, if you take a kilonewton and you divide it by a millimeter squared, you get a gigapascal. So that's just for shortcuts later on. Sound good? All right. Like I said, the calculus definition and that rigorous type of expression is not something we're going to use very much. It's mostly going to be force per area. Bless you. And then we'll discuss later when we get into things like when we actually start heavily discussing axial force members and things like that, why that's going to be a pretty valid assumption. Okay. So far, so good. Any general questions? Okay. I want to sort of get you all thinking about this a little more rigorously, and the only way really to do that is to look at an example. Now, I've got a pretty basic example. We're going to take our time with this because I know it's probably been a while since you've done this, but we're going to go through this example. We're also going to do it a little differently, and we're going to do things a little differently in this class than you're probably used to. For instance, you all have had statics. I'm sure you remember this whole IJK thing and dot products and cross products. Yeah, we aren't using any of that. We're just none of that. We're gonna sort of do some of our statics in this class a little bit differently, a little differently than you're used to. Ultimately, though, I think it's a little easier. That's just me. But we'll take our time with it and get into this. But what I want to do is I've got this 3-bar truss, which if you remember from statics, trusses are assumed to only have axial force. So they're either in tension, or either the elements are either in tension or they're in compression. So I'm going to go through and we're going to solve this truss, but we're going to determine the stress in each member. In other words, when I get a force in each member, I take that force, I divide it by the area to get the stress. So we'll assume each member is 4.5 square inches. So that's, if I took the element, and again I took either a samurai sword or lightsaber, depending on whether or not you're a sci-fi fan, cut a section and looked at that area, it would be 4.5 square inches. Sound good? Okay, all right. Now, they've re-imaged the computers, so let's see how the SmartBoard software works. Let's see. Let's see if this tends to cooperate with us. Does everybody have a copy of the notes? Those notes, that packet I gave you, should last for a little while because there's strain concepts in there and then just some general stress strain curve stuff later on. So we should be able to use those set of notes for a little while. Okay, let's see. Come on. Come on. Let me see something. My goodness. Software doesn't like me very much. All right, it comes down to it, I have tricks. I've tried this before and it worked. Going back to basics. Let's see if this works. Oh my goodness. Okay, that didn't work. I was using it a second ago, wasn't I? All right. Oh my goodness. Ooh, I'm not in a good mood right now. I made a promise that I was going to do everything on the SmartBoard. Now I'm getting this feeling like I'm not going to be able to. That's not working. Let me try something. Let's try and open the one I was working on. No. Oh my goodness, I'm not happy. All right, never mind. I'll see if I can figure something out on the YouTube playlist later, but for now, I guess I'll just use one of these markers and we will do it on the board. All right, I'm actually going to stop the recording and I'll add to this later or something. All right. So as you just saw, there were some issues with the SmartBoard software, so I decided to go through this example here in my office. This is just a PDF of the calculation, so I'll just go through these somewhat quickly since we were all there to review them in class today. So again, we have this 3-bar truss that you see right here, and the main purpose of this example is to determine the axial stress in each one of these 3 members. So the first step was to determine support reactions. Since this left support here at A is a hinge, we recognize that it has a vertical component and a horizontal component, so we call that AX and AY. We also have this vertical component at CY. Because it's a roller, that's obviously all we have. Here you can see the dimensions as shown. Note that the presence of the slope ratios that you can see right here, because that'll help us do a little bit of the underlying trig a little faster. Now, you saw in class today this sort of new way of doing the assessing the equilibrium of the structure with this table format. Basically, all it is drawing a table, and for instance, if you're looking at sum of moments, basically saying that all the moments that are clockwise have to equal all the moments that are counterclockwise, and just splitting them up individually. So to start off, sum of forces in the x direction, that was pretty straightforward. All we have is this 50 kip load going to the right and this AX going to the left. So AX has to be 50 kips going to the left. Now, summing moments at A, we know that that AX and AY
don't contribute any moment since they're going right through A. 50 kips contributes moment at a distance of 15 feet, and as you can see, that moment is clockwise, so we put that down here. And then 20 kips is also at 15 feet, and it's also going clockwise, so that goes right here. The only thing resisting that is this CY acting at a distance of 50 feet, and that's going counterclockwise. So we put that over on the right side, and then basically everything on the right has to equal everything on the left. Solve, and we get an answer of positive 21 kips, which indicates that since we assumed that the reaction was acting upward, that assumption was correct, and that means we have a 21 kip vertical reaction going upwards, and that's our answer there. For summing forces in the y direction, we basically just say everything going up has to equal everything going down. And we assumed that AY was going up, but when we do our computations, we get a negative answer, which means that AY is actually acting downward. So to summarize, here's all of the reactions. We have AX is 50 kips going to the left, AY is 1 kip going down, CY is 21 kips going up. Okay. Now, as for method of joints, we start off with joint A. We can really start off with any one of them, but just to keep it basic, we write our reactions at A in the direction that they are assumed. We indicate our slope ratio, and then what we're doing here is we're actually splitting this up into X and Y components. So we have an ABX and an ABY and an AC. This will help us do some things a little later that are easier. Now, for just looking at this on the face of it, we have 2 horizontal unknowns and 1 vertical unknown. That's a little bit of a misnomer, though. Keep in mind that these 2, they are unknown, but they're also related. So, but looking at this, we have looking at just on the face, this 1 unknown is pretty easy to solve for. If we've got 1 kip going down, we have to have 1 kip going up. So that's ABY is 1 kip going up. Our slope ratio indicates that ABY is to 1 as ABX is to 1, and that might be a little unclear. It'll make a little more sense in the next analysis when we have different numbers for our slope ratios. But that indicates that ABX is 1 kip as well, and it's also going to the right. Again, we've assumed everything here is in tension. Remember, these dashed lines indicate the unknowns, and these are all assumed directions. If you get a negative answer, no big deal. It just means that the assumed direction was incorrect. So summing forces in the X direction, if we have 50 kips going to the left and we have 1 kip going to the right, that means we need an additional 49. So this AC is 49 kips that's positive or 49 kips in tension, and AB, using the Pythagorean theorem, comes out also in tension, a little less or much less, 1.41. Going on to joint C, we do something similar. Now notice how I've assumed that this is compression just by observation. Now one of the nice things with this assessment is that I can just sum forces directly in the X direction, directly in the Y direction, and get 49 kips and 21 kips. But if you look at the slope ratios, you can see that the 49 kips is to 7 as 21 is to 3. It's sort of a check that everything you've done for the problem is correct. Go through and use Pythagorean theorem to get our force, and then we can summarize everything here. So that's the summarization of all the forces in the truss. We then need to go through and calculate the stresses, and that was sort of the whole point of this problem. Remember, we're saying stress is force per unit area. And since all the members have a 4.5 square inch area, we just take each of these members, divide it by 4.5 square inches to get our stresses, which we're going to express in KSI. So I guess you could say for the answer, this is the answer to the problem. But at the end of lecture, I did want to make another point about this to sort of emphasize the reasons for this topic and for this class. If I were to assume that this truss was made out of some, I don't know, aluminum alloy or some material, and for the sake of discussion, we'll say it has an allowable stress of 12 KSI, we can make some pretty interesting observations. One of them being that, for instance, member AB would be a member that's way over designed, significantly larger than it needs to be. We could definitely shave some some weight off of member AB. That's a definite plus. Now, if we another point is that while if we say sigma allowable is 12 KSI, technically all these members meet that, but if we want to incorporate some factor of safety, maybe members A, B, and BC need to actually be a little larger to meet an appropriate factor of safety. So this is where designs and the engineering decision-making process begin. That's one of the big motivations behind this course. So that's all I have for this example. Next time we will continue our discussion of stress and also begin to define the concepts of strain and how we can combine those two concepts to start to classify material behavior. And that's all. See you next time.